Okay, let's write down the general solution, and then we can see what this looks like. So, okay, our x3 column does not have a pivot position, so we can say that x3 is going to be a free variable, so let's assign it a parameter. Now x2 is going to be a basic variable because column 2 contains a leading 1, so let's write out the equation that corresponds to that row, which is going to give us x2 plus 7x3 is equal to 11. So solve for x2. You get 11 minus 7x3, which is the same as 11 minus 7s. Okay, then for column 1, x1 is going to be another basic variable because that column does contain a pivot position. It contains a leading 1, so it is a pivot column. So let's write out the equation that corresponds to the pivot row, which is the first row. So we get x1 plus 5x3 is equal to 8. Solve that for x1, you get 8 minus 5x3. Plug in your parameter, and you get 8 minus 5s. Okay, great. Now let's put everything together like we usually do. So let's use x as the variable vector, because remember, if it's a matrix equation, your variables, when you put them together, you actually get a vector x. So let's call that x. Let's use that symbol, and then we can expand it. Right out of this expansion, you're going to get x1, x2, x3. Okay, then let's put everything in. So we have 8 minus 5s, 11 minus 7s, and then s. And great. Okay, so now if you jump back up to an earlier example, what did we do at this point? We're essentially at this point, right? What did we do? We pulled out the s to write it in parametric vector form. We can't do that this time. It's not going to work out quite so nicely because s is not a factor of 8 minus 5s, and it's not a factor of 11 minus 7s either, right? Because of that, the 8 and the 11 kind of throw things off, so you can't just pull out an s. But here's what you can do. We can split this up into the sum of two separate vectors. I'm going to take one vector with all the constants, the parts that are independent of s, and then I'll take another vector that has all the terms that are dependent on s. So I got negative 5s, negative 7s, and then s. Right? That's certainly true. If you think about the definition of vector addition, and you add those two vectors together, you're going to get this vector. So that's certainly correct. But the payoff of doing that, why would you want to do it? Well, now if you look over here, we can treat this vector the same way we treated the one in the previous example where we pulled out the s. So here's how we can go to the next step. So this vector is going to be left alone. Then we'll pull out the s, and now we've got negative 5, negative 7, and 1 multiplied by s. So that's your general solution written in parametric vector form. Let's just put a box around this whole line. It kind of includes some of the steps, but it has the part where x over here, and we've got our final answer over here. It's a chain of equalities that connects those, so that's a good line to draw a box around. Okay, so that's our general solution. So notice we have this extra vector here that's added on. Unlike with the general solution to our homogeneous system up here, where we just had our general solution was just the set of all multiples of this vector. Well, now our general solution is kind of like the set of all multiples of this vector, but each of those multiples have to have this vector added onto them. So what that actually does is it shifts your solution set over a bit. Let's draw a picture. And let me write one more comment. Just to tie this together, let's tie this to what we set up here, where solutions to, if you add solutions, let me start over. If you add a particular solution to the matrix equation AX equals B to a particular solution to the associated homogeneous system, then the result gives you solutions to the matrix equation AX equals B. But it works the other way too. If you have a solution, your general solution to the matrix equation AX equals B kind of gets decomposed into a sum of two separate pieces. Here's the idea. This is a particular solution to the matrix equation AX equals B, and this is actually the general solution to ax equals 0. Let's add that in as a note. So this is a particular solution to ax equals b, and then all of this, and I'm putting a bracket because I want to include the parameter. This is the general solution to the associated homogeneous system, ax equals 0. Okay, and just because I'm getting obsessive here, I want to just be consistent. I'll put a bracket here as well. Okay, so that's the role that these pieces play, and we can emphasize that when we draw a picture. Let's draw two pictures. Let's draw first a picture of the general solution to the associated homogeneous system. So let's just draw a picture with all of these vectors. So just forget about the vector 8, 11, 0, and we'll just graph all the multiples of -5, -7, and 1. So just like we did before. So let's just do some labels here: x1, x2, and x3. And before I get too carried away, I want to make a copy of this so that we can do the other picture afterwards. Okay, so I'm going to draw a picture. Let's call this, we do a color yellow. Let's call, didn't leave myself much room here. Let me do this. Then I can do this. I can say, okay, call this vector, call that vector v, and call this vector p, which we'll use in a moment. But for now, all we care about is the v. Okay, so let's draw. What's this vector going to look like? -5 for an x1 coordinate, -7 for an x2 coordinate, and then 1 for an x3 coordinate. That'll look something like this again, kind of like our previous example. I'm not going to get too carried away with trying to make this precise. Just know that the x1 and x2 coordinates are negative, so it's kind of pointing behind the x3 axis, but then the x3 coordinate's positive, so it's going to have an upward, kind of like an upward inclination to it somewhat, but it's kind of hard to capture that in a drawing like this without adding a whole bunch of shadows and shading. But this isn't an art class, so I'm not going to worry about it too much. And then we want to extend this line, just like we did before. So what this gives you, and I'll just label this as the vector v, this is the general solution to the associated homogeneous system. So to ax equals 0. Okay, but what about now the general? So that's if we just graph all of this and we completely ignore this vector p, this point 8, 11, 0. So what happens if we now factor this point p in? Well, what we want to do, and I'm just going to use a different color here, just to let's draw the vector p as a position vector. So 8, 11, 0. So its x1 coordinate is 8 and its x2 coordinate is 11, and then its x3 coordinate is 0. So it's going to be like flat in the x1, x2 plane. It's going to look something like this. And I'm just going to move this arrow a bit so the stylus doesn't cause problems when I go to add the rest. Okay, so now what's going to happen, and I mentioned already that the effect of adding that one extra point on is that it shifts everything over. So I'm going to copy this, because now what I'm going to do, is just take this whole line and put it right here. Okay, that's the effect that adding that extra point on does. It translates everything over. Where's the, I'll just put the v back there. I'll label that v in because I didn't copy that when I brought the line over. Okay, so it has the effect of just shifting the entire line over by exactly the vector p, or that's sometimes called a translation. Okay, it translates the line by a factor of p. Okay, so let's label this now. This is the general solution to the original matrix equation, so ax equals b. So just to recap, if you just look at the general solution to the associated homogeneous system, and you have a particular solution to your linear system ax equals b, that's what this p really is. What you're going to do is you're going to translate the solution set of the homogeneous system by exactly your particular solution, treating it as a vector. And then the resulting picture, that's going to be a picture of the solution set to your original matrix equation, the one that's not homogeneous, the one that actually has a constant column that doesn't consist of all zeros.